Hello, my name is Pantelis, Chronis, and I will present our short paper, Link Prediction in Bibliographic Networks. A bibliographic network is a network that contains information regarding the publication process. From a data management perspective, a bibliographic network can be represented as an heterogeneous information network, in short, HIN. A HIN is a graph that contains different types of nodes and edges. For example, the HIN of a bibliographic network may contain authors, papers, and venues. The schema of a HIN shows the types of nodes and edges that exist in the network and how they are connected. The schema of the bibliographic network we study is shown at the bottom of the slide. An important concept in HINs is the metapath. A metapath is defined as a path on the network schema, and it corresponds to a sequence of node and edge types. For example, the sequence author-paper-author is a metapath that exists between two nodes when they are co-authors. Each path of the graph belongs to a single metapath. Metapaths are important because each metapath corresponds to a relation with a particular meaning. Link prediction is the task of modeling and predicting the formation of edges in a network. Predicted edges may correspond to relations that exist in the real world but have not been observed in the dataset, or to relations that do not exist but are likely to be formed in the future. On a bibliographic network, link prediction can be useful for providing recommendations and for gaining insight into the publication process. Algorithms for link prediction in HINs can be divided in two main categories. An example of the first category is Metapath Counts algorithm. Metapath Counts works in the following way. Given a pair of nodes, U and V, the algorithm finds all paths up to length L that connect the two nodes. Then it groups the path according to their metapath and counts them. In this way, it obtains a vector with the number of occurrences of each metapath between two nodes. This vector is given as input to a simple classifier that predicts the probability that an edge exists between the nodes. The classifier is trained using pairs of nodes with edges as well as pairs without edges. An example of the second category of link prediction models is Metapath to Vec. Metapath to Vec assigns a vector representation to each node of the network. These representations are called node embeddings. The probability that an edge exists between two nodes is estimated as a function of their embeddings, specifically as their Euclidean distance. So, an edge is more likely to exist between two nodes when their embeddings are close. The algorithm obtains these representations by performing multiple metapath-constrained random walks on the graph. When two nodes are encountered close by on a random walk, their embeddings are adjusted so that their distance decreases. Pairs of nodes without an edge between them are sampled randomly from the graph, and their embeddings are adjusted so that the distance increases. We evaluate the two models on a sample obtained from the DPLP dataset, which contains authors connected to the papers they have written, which are connected to the venues they were published. Each model is applied on a large number of node pairs, some having edges between them and some not having. For each pair, each model calculates a score for the probability that an edge exists between the nodes. The desired outcome is that pairs with edges between them are assigned higher scores than pairs without edges. We evaluate this outcome using three measures, based on ranking the pairs according to their scores. For min rank and MRR, the optimal value is 1, and for hits at 10, the optimal value is 10. The evaluation is performed for each of the two edge types of the dataset separately. As we can see, Metapath Counts achieves better scores on both edges and for all three metrics. In conclusion, the simpler model, Metapath Counts, achieved a better outcome. A few possible explanations for this observation are the following. First, Metapath Counts has fewer parameters to learn. This means that it can be trained more effectively with the number of edges per node that exist in the network. Second, Metapath to Vec requires a selection of several hyperparameters, like the number and length of random walks, the learning rate, and the number of training iterations. Tuning these hyperparameters is not straightforward and is performed heuristically. Third, it is possible that the patterns modeled by Metapath Counts are sufficient to model most patterns that exist in the network. Finally, the results may also be affected by particular characteristics of the dataset and the sample we selected for the evaluation.